Hello, my name is Donovan Gray, and this is my lab report of the third lab on circuits. A little bit of an introduction. This lab was a purely experimental lab, only there was no coding aspect to this. And it was about building circuits and using the equations we have in class, specifically around the change in potential across different circuit elements and Kirchhoff's laws to predict the behavior of circuits with resistors in series and resistors in parallel, and then also use multimeters to measure the actual values of conventional current and potential differences in the circuits, and then examine how the behavior of the ohmic resistors and capacitors are affected, and then also using the Kirchhoff's laws of voltage and current, we can do math to find experimental values for these different quantities. And of course, there's always going to be error in the electrical components because as batteries are used, of course, their voltage drops over time and wires can be faulty, resistors can be a little faulty, ammeters can be not calibrated. So there are a bunch of different pieces of error that are associated with this lab. So for the relevant equations, we have the potential change across the resistor of V or delta V, but V simplified, equals IR, Ohm's law. Capacitor potential change, V equals Q over C. Delta or sigma V equals 0. So the sum of the potential from inside the circuit going in any loop direction should and always is 0. And the sum of the current going into a junction equals the sum of the current going out of a junction in magnitude. So for the first setup, we have the following circuit diagram as well as the picture of the circuit. It's a little messy, but for the VR1, which is responding to the resistor that appears right after the first ammeter, and right after I1 going in the clockwise direction of 47 ohms, we have a potential drop of negative 0.8 volts. And over the 100 ohm resistor, we have a potential drop of 1.8 volts. And when we go back up to the battery, we add a potential increase of 2.6 volts in that loop. And the calculated current was 16.9 milliamps. And the theoretical value for the EMF should be 3 volts. Of course, you have two 1.5 volt batteries. The two should be equated to 3 volts. However, like I said, as batteries are used over time, their voltage drops, and that's why we see the slight discrepancy. However, the Kirchhoff loop rule still applies here. 1.8 plus 0.8 is 2.6, and so when we go in a full loop, the sum of the potential differences is 0. And the ammeter is only a wire. It's really effectively not a resistor in the ideal model. And so when we connect it in parallel, the ammeter in at I1 displays the exact same current as the ammeter in I2. That shows both that the ammeter itself does not affect the current, but also that resistors in series do not affect the current. So as the current goes over both resistors, the current stays the same. The current is the same in the entire circuit. And then there's a diagram below the circuit diagram that shows, or a graph that shows the changes in potential at the different circuit elements. So at the beginning, going through the batteries, you get an increase in 2.6 volts, then it stays as it goes along the wire, drops 0.8 volts as it goes over the first resistor, stays over the wire, and then drops another 1.8 volts, and then stays the same over the ammeter. In the second setup, it was after we charged the capacitor and we connected the capacitor to the resistor. The relevant differential equations that describe the current over time are displayed there. Basically, if you graph the natural log of the first potential over the potential over the initial potential, it should give a straight line of negative t over RC. And at time RC, the potential should be at 1 over E of its original value, since V scales directly with Q, and you can see in the equation right there, when T is RC, the proportion between them is 1 over E. When the battery was connected with the capacitor in the circuit, the bulb faded with brightness as time went on. And then when the capacitor was connected to the bulb without the battery, the bulb also faded as time went on. And based on that equation, you can see as time approaches infinity, the charge approaches 0 when we have a capacitor connected to a resistor. which explains why the battery went out, because as the charge goes down, the current goes down. As current goes down, brightness goes down. What if questions, if a charged capacitor with no resistor was in the current, it would take 0 seconds for it to fully charge. Now, this is unrealistic because, of course, wires do carry resistance. In our models, we assume that they don't, that they are ideal wires and they carry no, or they have no resistance. But of course, all wires in real life carry resistance, and no capacitor can be instantly charged or discharged. That would mean infinite current, and that is not a real thing. But that's it.